Some of the light hitting your eyes tonight left its source before Earth existed. That's not a metaphor. That's the literal content of the night sky. Here's the part that doesn't get said cleanly enough in most of the videos covering this topic. Some of that light source is already gone from us. Not destroyed, not moved, just permanently placed somewhere we can never reach again under any technology given any amount of time. We've spent 2 episodes proving that reaching another star system is staggeringly hard. This episode isn't about hard. A significant fraction of the galaxies currently sitting inside our observable universe are already unreachable. Even if you could travel at the speed of light itself, starting today, not because the distance is too far across, but because the space between here and there is stretching faster than anything, light included, can close it. Footnote 1. Give it enough time, and that number doesn't shrink. It only grows. This is the same measuring instrument problem this channel has been circling since the sub-series began. We keep judging the universe by the only ruler we have, which is ourselves, on human timescales. Here's the universe answering on its own clock instead. And the answer isn't difficult. It's closed, permanently, on a schedule you don't get a vote in. For answers to the Fermi paradox got us this far. Here's the one nobody asked for. Even solving all 4 doesn't buy you the whole universe. It buys you a shrinking room. The hard math simplified. Here's the equation, because this show doesn't get to say the universe is expanding and move on. In 1929, Edwin Hubble found that a galaxy's recession velocity is directly proportional to its distance from us. V equals h times d. Velocity equals the Hubble constant times distance. That's it. That's the entire law. The farther away something is, the faster the space between us and it is stretching. Not because the galaxy is moving through space under its own power, but because space itself is expanding, carrying the galaxy along with it. Plug in real numbers. Using h at roughly 70 kilometers per second per megaparsec, a commonly used round value. More on the actual dispute over that number in a moment. Solve for the distance at which recession velocity reaches the speed of light, and you land at approximately 14.5 billion light-years. Footnote 2. That boundary is called the Hubble sphere. Past it, galaxies are already receding from us faster than light, right now, and this does not violate relativity, because nothing is moving through space faster than light. Space itself has no speed limit. Only things moving through it do. Here's the number that actually earns this episode's title, though, and it's a stricter one than the Hubble sphere. Because cosmic expansion is accelerating. Because there's a component of the universe, dark energy, whose density doesn't dilute as space grows. The Hubble sphere itself doesn't expand fast enough to ever let a photon from beyond a certain distance catch up to us. The target keeps outrunning the light, chasing it permanently, not just for a very long time. That distance is called the cosmic event horizon, and per the widely cited 2005 calculation by astronomers Charles Lineweaver and Tamara Davis, its current proper distance is 16 billion light-years. Footnote 1. Anything beyond that line, right now, could send a photon directly at us at this exact instant, at the actual speed of light, and that photon would never arrive. Not eventually. Never. Worth being honest about the number that goes into this calculation, since honest uncertainty is this show's whole deal. The exact value of the Hubble constant is not settled science right now. Measurements from the early universe, using the cosmic microwave background, land around 67. Measurements from the local universe, using nearby supernovae as distance markers, land around 73. Footnote 3. That gap, the Hubble tension, is one of the more genuinely unresolved puzzles in cosmology at the moment, and it shifts the exact location of these horizons by a meaningful margin without changing the underlying argument even slightly. There is a wall. It is not an engineering problem, and it is measured in billions of light years rather than kilometers per hour. Though, what is extremely fascinating, the calculation does not describe an object outrunning a pursuer. It describes the space between them expanding at a rate a pursuer cannot outpace, regardless of the pursuer's own velocity. It would be illogical to call this a limit on travel. It is, more precisely, a limit on the concept of arrival. The difference between far and gone. Here's where the popular explainers usually collapse three different distances into one, and the collapse is exactly the kind of thing this channel exists to untangle. There are three separate horizons in play, and confusing them is apparently common enough that two astronomers wrote an entire paper in 2004 just to keep other physicists from doing it. First, the particle horizon, the edge of the observable universe. Everything whose light has had time to reach us since the Big Bang. That's currently about 46 billion light-years away. Footnote 4. Second, the Hubble sphere from Section 1, about 14.5 billion light-years, the current boundary of faster-than-light recession. Third, the cosmic event horizon, 16 billion light-years, the true point of no return. Footnote 1. Three numbers, three different meanings, and only one of them tells you what you can never, under any circumstance, reach. Here's the genuinely strange consequence of having three different horizons instead of one. Some of the galaxies we can see right now, tonight, through a telescope, have already crossed the cosmic event horizon. Footnote 5. We're not looking at them as they are. We're looking at light that left them before they crossed the line, light that's still arriving, still legally ours to observe. But any new light those galaxies emit from this point forward, starting now, this second, will never reach us. We'll keep watching their past for billions of years after their present has already become permanently unavailable to us. One physicist's calculation puts a number on how much of the universe this has already happened to. Of an estimated 4.7 trillion galaxies that will ever be observable across cosmic history, roughly 4.634 trillion of them are already permanently unreachable, even at the speed of light, leaving only about 66 billion still within reach. That's not a future problem. That's the current standing balance. And it does not go one direction only in a comfortable way. Every second that passes, more galaxies complete the crossing permanently, with no ceremony and no way to reverse it. Footnote 5. I am able to observe galaxies whose present I will never be able to observe. I am uncertain whether watching something's past while its present becomes permanently unavailable is a phrase that exists outside of cosmology. I suspect it should. Why engineering alone won't save you. 2 episodes ago in The Light Speed Isn't a Speed Limit. It's a wall episode where we discuss the Alcubierre warp metric, a real solution to Einstein's equations that would, in principle, let a ship travel faster than light by moving a bubble of contracted and expanded space-time around itself rather than moving through space-time directly. Footnote 6. It's worth asking directly. Does that solve this problem? Does a working warp drive get you past the cosmic event horizon? No. And the reason why is worth sitting with, because it's not an engineering limitation, it's a definitional one. The cosmic event horizon isn't the distance light can't cross, because light is too slow. It's the distance beyond which no signal of any kind, moving at any speed up to and including the speed of light, can ever arrive, because the space it would need to cross is growing faster than the signal can close it, and that gap widens without limit the longer the signal is in transit. Footnote 1. A warp bubble is still, from the outside, a physical object making a trip through an expanding universe. It still needs to close a distance that is past the horizon, actively growing away from it faster than anything, including a hypothetical warp bubble, could shrink it forever. Footnote 7. Exotic propulsion solves the speed problem this show already covered. It does not solve the geometry problem this episode is about, because the geometry problem was never about speed to begin with. It was always about whether the destination remains part of the same causally connected universe as the traveler, and past this line, it simply isn't, regardless of how fast anything can go. This is the same correction part 2 of the physics block, made at a smaller scale, just escalated. Relativity doesn't forbid speed, it forbids causal contact. Here, the escalation is total. It's not that reaching another civilization is difficult, or that reaching another star is difficult. It's that reaching most of what currently exists in the universe, right now, is not a difficulty at all. It's a closed question, answered by the geometry of space-time itself, before any engineer, however brilliant, ever gets a turn to try. Then there's the countdown that no one advertises. Run this forward, and the picture gets starker rather than stabilizing. The local group, our own small cluster of gravitationally bound galaxies, including Andromeda, which is on a collision course to merge with the Milky Way in a few billion years, stays with us. Gravity binds it together tightly enough that cosmic expansion never pulls it apart, the same way cosmic expansion doesn't stretch the solar system or your own body apart, because locally bound systems simply don't participate in the metric expansion of space the same way unbound galaxies do. Footnote 8. Everything else is a different story. Cosmologists modeling the far future of a universe dominated by dark energy. We're going back to a widely cited 2000 paper by Lawrence Krauss and Glenn Starkman on the long-term fate of life and observation in an accelerating universe. Describe a genuinely strange endpoint. Roughly 100 billion years from now, an observer in the local group's remnant galaxy would look out and see nothing beyond it all. Not very little. Nothing. Every other galaxy will have crossed the event horizon. Its light redshifted into undetectability long before that, until the entire rest of the universe becomes observationally indistinguishable from empty space. An island universe, mistaking itself for the whole of creation, with no way to know, from the inside, that it was ever wrong. Footnote 9. Here's the detail that should sit uncomfortably. This isn't a distant hypothetical happening to some future civilization. It's happening right now, continuously, at this moment, while you watch this video. Somewhere, some galaxy just completed its crossing. It happens every second, whether or not anyone is around to notice, whether or not anyone ever builds a telescope capable of watching it happen. Footnote 5. So if life can find a way to build a species clever enough to calculate exactly how much of the universe it's already lost in real time, while the universe continues losing more of it during the calculation, it may be very efficient, but it seems also deeply rude. This channel spent an entire sub-series on a single premise. We are the measuring instrument, and everything we know about life is one data point, measured against ourselves. This episode is the same argument at a different scale. We built the idea of the universe out of what we can currently see and, more optimistically, what we assumed we could eventually reach. Both of those turn out to be moving targets, and the second one is shrinking. Go back to the 4 answers this channel spent a whole synthesis episode naming: detection, timing, population, geometry. Geometry was framed correctly as the answer to why we might never meet another civilization. Here's the scope this episode adds, and it has nothing to do with whether anyone else is out there at all. Even in a universe with no other civilizations whatsoever, even if the rare Earth hypothesis turns out to be completely right and we are, in fact, entirely alone, the overwhelming majority of the universe is already a place we will never visit, never observe as it currently is, and never in any way causally affect, regardless of loneliness or company. This isn't a Fermi paradox answer. It's something underneath all 4 of them. Whether or not the room has other people in it, the room itself is shrinking, and there was never a version of Solve the Engineering that changed that. And yes, as always, there's still a lot of universe left to look at. Most of it, as of tonight, is already a place we will only ever see as it used to be, never as it is. That's a strange thing to sit with, and it doesn't get less strange with practice. Here's the part that's oddly grounding, though none of this changes anything about tomorrow. The light still arrives. The math still works. The local group is still here, still bound together, not going anywhere for a very long time. We were never going to see all of it. We get to see an honest, well-measured fraction of it instead, and there's still a lot of that left to look at. Next time, what happens to the fraction we do keep over a timescale so long that even permanent starts to look temporary? It's a Tuesday, and we will continue to stare expectantly up at the universe, looking for answers we may never find.